So hi everyone, welcome to my channel. So in this video we are going to talk about a very small topic, that is the application of elastic behavior of materials with regard to the chapter mechanical properties of solids. Okay. Now first thing is example is crane cable. Actually basically this application of elastic behavior is discussion of three examples. Okay. So the first example is crane cable. Okay. Now in the crane cable, suppose load of 10,000 kg is to be lifted. Now normally the yield strength, yield strength of the steel cable, it is around 300 into 10 power 6 Newton per meter square. Now yield strength is in the stress strain graph we have seen that this is the maximum value of the stress that can be applied on the given wire or material so that it doesn't lose its elastic properties. Okay. So that limit is 300 into 10 power 6 Newton per meter square. Okay. So that means this is the maximum stress. This is the maximum stress that can be applied on the steel wire. Now stress is force by area. Okay. So from that we can calculate the area. This is the area. Okay. This is the area. So area is force divided by this yield strength. Now force is, this is load. So force is simply m into g. Mass is given. So 10,000 into g divided by 300 into 10 power 6. Now on simplifying this we get 3.3 into 10 power minus 4 meter square. Okay. Now this is the cross sectional area. So area is equal to pi r square. So from that we can get the value of the radius. Now this radius comes out to be around 1 centimeter. Okay. So that means 1 centimeter radius thick wire is sufficient to withstand this stress. Okay, but suppose we take a margin. Okay, like suppose we take, instead of 1 centimeter we take it to be 3 centimeters, so that we are within the safer limit. Okay, now again in order to further increase this strength, what we do, we use a term braid. Braid means this wire, multiple wires are wound together. Okay, so that to further increase the strength. Okay. So this is one example. Second example is this bending of beam. Now this is a beam of length L and suppose weight is W. So this bending from this equilibrium position is delta. Okay, from this equilibrium position it has come down through delta. So now if D is the depth of the beam and B is the breadth. Okay, so this is B is breadth, D is depth. Then the bending, it is given by the expression, this delta is the bending. Okay, so this is given by W L cube by 4 BD cube Y. So W is the load. Okay, now obviously as you can see, delta is inversely proportional to Y. So that means now normally what we will want for a beam, good beam, it should have low amount of bending. So minimize bending. Materials with high value of Young's modulus means if this quantity is high, obviously delta will be small because delta is inversely proportional to Young's modulus. Now another factor is this B and variation in B and D. Now obviously if we change the value of D, okay, if we increase D, again delta will decrease. Okay, now here a comparison may be made like whether to change B or D. So changing D will be more effective. Changing D will be more effective because we have a term DQ. So if you change D, DQ will be further increased. If you increase the value of D, DQ will be further increased. So thereby decreasing the value of delta. Okay. Now normally these beams are made of this shape, I shape. This is I shape. Okay. Now why this is done? To avoid buckling. Okay. Now this term buckling means this bending. Bending means buckling. Okay. And it also gives large load bearing surface. This structure gives large load bearing surface. Okay. Now the third example is the structure of pillar. Now pillar can be designed like this, means this is the floor part and this is ceiling part. Okay. Or you can have a pillar like this, where this part is, this area is increased. Now if you increase the area, what is the benefit? The load gets distributed. Okay. So this is with regard to designing of pillars. Okay. So these are three examples illustrating the application of elastic behavior of materials. Okay, so this discussion is entirely based on from your NCERT textbook. Okay, so I hope these things are clear to you. So now this is a small discussion about the maximum possible height of a mountain. Okay, now we know that this Mount Everest, it has a height of 8848 meter. Okay, then there is a mountain called Mount Denali. Mount Denali, it is in North America. Now its height is 10204 meter. Okay, but this mountain is like large part of this mountain is within water. Okay, so from this point to this point, the height is this 10204 meter. Now regarding Mount Everest, it is completely above water. Okay. Now, so the discussion point is what can be the maximum height of a mountain. Now suppose this is the structure of the mountain. So this mountain is of height h. So the force per unit area at the bottom, this part, the force per unit area will be h rho g. Okay. Now force per unit area, this term is just like pressure. This is just like pressure. Force per unit area is pressure. So obviously this pressure will act in all directions. So it will act in sideways also. Okay. Now, so it will act sideways. That means this rock, which should be able to withstand this pressure. Okay. Now, elastic limit of rock is 30 into 10 power 7 Newton per meter square. 30 into 10 power 7 Newton per meter square. This is just an average value. So that means this is the maximum pressure that the rock can handle. Okay. So that means if we equate these two quantities, so we have h rho g is equal to 30 into 10 power 7. Now rho is density of rock, so that is 3 into 10 power 3 kg per meter cube. So simplifying this, we get h equal to 10,000 meter, or we can write 10 kilometer. Okay. So that means this is the maximum possible height of a mountain. Okay. Now Mount Everest, it has a height of 8848 meter. Okay, but then you will say that Mount Denali in North America, it has a height of 10204 meter. Okay, so how is that possible? Because just now we have obtained that 10,000 meter is the limit, or 10 kilometer is the limit. This mountain is greater than 10 kilometer. Okay, the reason is, see, normal mountain which we are talking about, this at the base it is experiencing a force per unit area equivalent to this quantity. Okay. Or h rho g, where h is the height. Okay. Now for Mount Denali, more accurate, 4207. This height is 4207 meter. So more than, not more than, but 4207 means almost 40% is inside water. So when water is there, so this water will also exert a pressure in this direction. Okay. So that will increase the pressure bearing capacity of the rock, these rocks. Okay, so for that reason this height is slightly greater than 10 kilometer. But otherwise, for normal mountain which is above the ground level, the maximum possible height is 10 kilometer. Okay, so I hope this concept is also clear to you. Okay, so in case of any doubt, you can comment. I will do clarify. Okay.